Imagine for a moment that the universe you see above your head every night, with its billions of galaxies stretching endlessly into the darkness, is hiding a secret so profound that even the most brilliant minds of physics are left puzzled. A force that you cannot touch, cannot see, and cannot measure directly, yet it dominates everything you know. It is everywhere, all around you, and without it, the universe would not look the way it does right now. Scientists call it dark energy, and the mystery surrounding it is one of the greatest unsolved puzzles in human history. But what exactly is dark energy, and why is it so important? To answer that, we must go back in time to the very beginning of modern cosmology and walk through a story filled with suspense, discovery, and unanswered questions that shake the foundations of science itself. In the early 20th century, Albert Einstein developed his general theory of relativity, a framework that described gravity not as a force, but as the curvature of space and time. When Einstein applied his equations to the universe as a whole, he realized something troubling. His mathematics suggested the universe should not be static, but should either expand or contract. At that time, the prevailing belief among scientists was that the universe was eternal and unchanging. To correct what he thought was a flaw in his equations, Einstein introduced what he called the cosmological constant, a kind of repulsive energy built into space itself that countered gravity and kept the universe balanced. He later called this his biggest blunder, because soon after, in the 1920s, Edwin Hubble observed that distant galaxies were moving away from us. The universe was not static at all. It was expanding. For decades, scientists believed that the expansion of the universe triggered by the Big Bang must be slowing down over time. After all, gravity pulls matter together, and with billions of galaxies filled with stars and dark matter, it seemed obvious that expansion should decelerate. But then came the shocking discovery of the late 1990s that changed everything. Two teams of astronomers, studying distant exploding stars called Type Ia supernovae, measured their brightness and distance to calculate how the universe had been expanding over billions of years. What they found defied all expectations. Instead of slowing down, the universe's expansion was speeding up. It was as if some invisible force was pushing galaxies apart, stronger than the pull of gravity itself. That mysterious force was named dark energy. This revelation was not just surprising, it was terrifying. Because if the expansion is accelerating, then the universe is on a path far stranger than anyone had imagined. Scientists now estimate that dark energy makes up about 68% of the total energy content of the cosmos. Dark matter, another unseen component, contributes about 27%. And everything we know, stars, planets, dust, gas, and even you and me, makes up less than 5%. In other words, everything visible is just a small fraction of reality, while the vast majority is completely invisible and mysterious. The universe is dominated by something we do not understand, yet it determines its ultimate fate. But what is dark energy really? Here begins the suspense. One possibility is that Einstein's cosmological constant was right all along. That space itself possesses a constant energy density that stretches it outward forever. This explanation is simple, elegant, and mathematically consistent. Yet there's a problem. Quantum physics predicts that empty space should be full of tiny energy fluctuations, called vacuum energy. But the amount predicted by theory is so unimaginably huge compared to the observed value of dark energy that the mismatch is absurd, off by a factor of 10^120. This is the worst theoretical prediction in the history of science. So if the cosmological constant is real, why is it so small compared to what physics tells us it should be? Other scientists propose that dark energy is not constant, but dynamic. They call this idea quintessence, a new kind of energy field that changes over time and space. Unlike a fixed cosmological constant, quintessence could evolve, growing stronger or weaker, influencing the future of the cosmos in unpredictable ways. But what exactly this field is made of remains completely speculative. No experiment on Earth has yet been able to detect such a field, if it even exists at all. Still, the possibility opens the door to a universe that is far more flexible and strange than we can currently imagine. Another radical idea is that dark energy does not exist at all. Maybe what we call dark energy is simply our misunderstanding of gravity itself. General relativity has passed every test so far, from predicting black holes to explaining gravitational waves. But perhaps on the largest cosmic scales, the rules of gravity are different. Modified gravity theories attempt to explain the accelerating expansion without invoking any mysterious energy. If true, this would mean Einstein's theory, while accurate in many ways, is incomplete. That possibility is both thrilling and unsettling, because it suggests that the very law we thought governed the universe may be hiding a deeper truth. The stakes are enormous, because the nature of dark energy determines the fate of everything. If dark energy is constant, the universe will continue to accelerate indefinitely, stretching galaxies so far apart that eventually each one will become isolated in a cold, empty void. This scenario, known as the Big Freeze, ends with stars burning out, black holes evaporating, and nothing but darkness remaining. If dark energy grows stronger over time, the acceleration could rip galaxies, stars, planets, and even atoms apart in a catastrophic event called the Big Rip. Imagine the very fabric of reality tearing itself to pieces. On the other hand, if dark energy weakens, gravity could eventually regain control, halting expansion and pulling the cosmos back together in a fiery collapse called the Big Crunch. The universe's destiny depends entirely on what dark energy turns out to be. To unlock this mystery, scientists have launched ambitious projects. Telescopes like the Hubble Space Telescope and the more recent James Webb Space Telescope are mapping distant galaxies to track how expansion changes across cosmic time. Large surveys such as the Dark Energy Survey and the upcoming Vera C. Rubin Observatory aim to chart billions of galaxies, searching for subtle patterns in their distribution that could reveal dark energy's fingerprints. Space missions like the European Space Agency's Euclid telescope, launched to study the geometry of the universe, are designed with one central goal: to understand dark energy. These projects represent humanity's attempt to answer a question that could redefine everything we know about physics. Yet despite all these efforts, the nature of dark energy remains elusive. Every new observation deepens the mystery, rather than solves it. We see its effects in the way galaxies drift apart, but we cannot capture it in a laboratory, cannot bottle it, cannot manipulate it. It is like a ghostly presence, shaping the cosmos from the shadows. And here lies the suspenseful truth. The universe may be far stranger than we ever dared to imagine. Perhaps dark energy is not a single phenomenon, but a sign that our entire picture of reality is incomplete. Perhaps it is pointing us toward a new revolution in science, just as the discovery of relativity and quantum mechanics reshaped the 20th century. For now, we are left with more questions than answers. Why did dark energy begin to dominate the universe only in the last few billion years, long after the Big Bang? Why is its density so small yet so precisely tuned that it allows galaxies, stars, and life itself to exist? If it were slightly stronger, matter would never have formed into complex structures. If it were weaker, the universe might have collapsed long ago. The fact that we are here at all contemplating this mystery suggests that dark energy is not just a random accident. Some call this the cosmic coincidence problem. Is it luck, or is there a deeper principle at play? Could the universe be fine-tuned for life? Or are we just one of countless universes in a vast multiverse, each with different values of dark energy, and we happen to live in the one that allows observers like us to exist? The suspense deepens when we realize that our time to investigate may be limited. As the universe continues to expand faster and faster, distant galaxies will move beyond our cosmic horizon, disappearing from view forever. In the distant future, astronomers will no longer see the vast cosmic web we observe today. They will be trapped in an island universe, surrounded only by the remnants of the Milky Way and its neighbors, unable to know the truth of cosmic history. The fact that we live in a moment when the universe is still visible in all its grandeur is a gift, and perhaps a clue that our generation is meant to uncover the secrets of dark energy. So what is dark energy? A cosmological constant? A new force of nature? A sign that gravity itself is incomplete? Or something so alien to human understanding that our current physics cannot even describe it? The answer is still hidden, but the search continues. Every telescope pointed at the night sky, every experiment probing the laws of physics, every mind daring to ask the deepest questions, all are drawn toward this ultimate mystery. Dark energy is not just a scientific puzzle. It is a reminder that the universe is far greater than our imagination, that there are truths waiting in the darkness, beyond the reach of our senses, whispering to us through the silent expansion of space. The story of dark energy is far from over. It is the beginning of a journey into the unknown, and perhaps when we finally uncover its nature, we will not only understand the universe, but also our own place within it.